afternoon, everybody. Sometimes my Safari internet browser gets a hiccup, and when I'm logged on to Blackboard too many times, just does something strange that I cannot navigate. So I'm finally back in there, and I'm going to start recording this lecture, as somebody will not be able to attend, and share my screen with you guys. Very good. Start asking how you guys are doing. How's everything? Anybody doing badly? Stress. That thing is gonna kill us one day. So you have to actually start learning the tools for that. I started this almost 20 years ago. I realized that my normal driving was, rather fast, and I was doing funky things, going left and right and passing people left and right. And one day I told myself that actually none of this stress will happen if I just drive always below speed limit and just follow the cars and go wherever they go. And that's what I've been doing so far. Occasionally I find my way home, but hey. So this COVID is going to kill us, if not the stress, but there is not much I can do about that. So what I want to do today is I looked at this particular topic of sequential linear programming, and it's used for laminate design. And it's an important topic enough that I think I'm going to make my second test, which will be also like the project that you had before, to design your laminate using sequential linear programming. That, of course, means that I cover the derivative calculations well enough so that you can linearize the problem at any point you want in the design space, and be able to construct a linear approximation and call the linear programming or integer linear programming, for that matter, and get a design and look at the new design and decide if you're gonna re-linearize the problem and do one more step. And that way you can potentially find the best design. Now, rather than doing this for any arbitrary problem, I'm just going to actually ask you to do the same problem that you've done in test one, because then you have a target design that you know for a fact that particular design is one of the best. Now, there is a fair amount of chance that this approach is not going to work for that problem that you solved manually. And the reasons for that is some of it we already discussed. We talked about it. And some of it may have an additional angle, additional feature to it that I think it's also important to find out. And for that reason, I've decided on that project as your second test. And unless, of course, there's a unanimous disagreement that you want me to change that to something else, either a real test where we ask questions about individual steps and things like that, or whether we do this or a similar problem is up to you. I always leave that choice to you guys. If there's enough, inclination one way or the other, I'm more than happy to go along with that. So what's the best thing that I can do? I can actually start solving a problem similar to what you've done, except it's a different problem. That will include 0 and plus minus 45 and 90 degree angles. And if I want to make all the angles variables, it'll become potentially complicated. So instead, I'm going to be using the number of zeros and number of plus minus 45s as the design variables for this for my implementation. Also, in terms of the failure criteria, you've been using psi Hill, and what I will do is probably I will demonstrate this for max stress, max strain type of approach. So in terms of the keeping track of the constraints, you'll have a little bit more to handle in the notebooks that I'm going to be working on and will be providing to you, so that you can benefit from those notebooks that I'm going to be preparing. One thing I definitely want to emphasize, and I want you to follow this emphasis. Please do not just copy my own notebook and change things and give it back to me. First of all, I don't need to see anything that I wrote in there as explanations. You want to write your own explanation, do so. But if there is redundant, don't write. In terms of how you sequence the computations, if there are unnecessary steps that I'm using in my notebooks just to demonstrate the approach and make comparisons, you don't need to give me those back again. You can delete those, use only the lines that you will be needing. So it's important that you follow this direction in doing the test too. So I'm talking a lot without showing what I'm going to be doing. I'm going to come to that in a minute. But before that, let me ask you if there are any thoughts about what I just said, and any questions about what I just said. Floor is open for questions. No questions? I'm looking at my dingy-donky thing, no dings and dongs. About the stress, Harrison, I gave you the example of my driving. That was actually a bad example in this particular case. I just looked at your sentence that says projects and tests, so you're stressed. That doesn't mean that you just leave the tests and projects without doing them and be happy about it. That was a wrong, I think, comparison. In that particular case, what you do is what I always do, and that is, you show what you know. You just do what you can do best, and let the judge, who's reading your test or who's evaluating your project, decide if your effort was genuine and you were just trying to solve the problem in hand rather than trying to pull things off the air. So even if it's not complete, if you actually show the effort, most instructors and most evaluators like this are experienced enough that they will see whether you're really trying to solve something by genuinely showing the effort, or you're trying to pull things off the thin air. This is true, gentlemen, for everything that you do in course evaluations, class evaluations. When I say evaluations, meaning that the evaluation of your effort. As I said, most instructors are experienced enough that if you show the interest in solving the problem and demonstrate that there is a genuine effort, you're not going to be penalized a lot. At least not in my case. All right, so with that, let's get back to the topic. The lecture for this was actually, although I'm going to pull this lecture 11 one more time and show it very, very, very quickly, which was the use of the sequential linear programming for solving nonlinear problems where we're talking about the stress and strain calculations in laminates. So we said that any linear program can be turned into, through the Taylor series expression, into a linearized form where you will need the derivatives of the objective function and constraint first order derivatives. Nothing more than the first order derivatives. These are essential to be able to linearize the problem. And this is what's going to enable us to make approximations to the original nonlinear functions at a specified design point, x super 0 or x volte-face x sub 0. This is the base design, and you're making an approximation to this problem in this form at that point. If this point changes, these quantities are going to change. These quantities that I'm circling around partial derivatives of the nonlinear functions with respect to variables have to be evaluated at the base point. These are going to change. So at every new design point, you have a new derivative information that you can construct an linear approximation. If you have this, then a problem like this, which has nonlinear constraints of that form, can be turned into a sequence of linearizations. This is linearization number 1, linearization number 2, linearization number 3 in here. You see that the solution of the linear problem is approaching the nonlinear problem. So that's at least basically the purpose. In case of composite design, we said typically the objective is weight. So it has some sort of a count of total thickness multiplied by density. You can take this density if it's constant outside, and it does not influence the minimization activity at all. You can completely delete it, or you can put a number in there. You always get the same answer. And then the constraints, which are now in terms of base strains in the principal applied directions. They can be also stresses along principal applied directions. But once you have the strains along principal applied directions, you can always compute the stresses very easily by doing the sigma equals E epsilon kind of thing, where in your case, E will be the transform reduced stiffness matrix. So this is what we're going to be doing. And we did some derivation, and we showed that the derivatives of the principal material direction strains with respect to thickness variables, applied thickness variables, are actually nothing but derivatives of the mid-plane strains multiplied by the transformation matrix. And the question is, how do you compute the derivatives of the plane strains? And that was from the governing equation. We came up with an expression like this. This is the key expression that we're going to be that will be needed to make the linear approximation. And the thickness information in there is buried into the A matrix and buried into the epsilon naught. So we will see how this is going to be computed in the tutorial that I'm going to start right now. Questions? No questions so far. So is that last equation the same as the stress calculations or close to it? Yes, indeed. In fact, once you compute let me minimize this and get back my PowerPoint chart. Where did it go? Here. If you have this expression, what you will do, you will put this into the right-hand side here. Okay? And what that will give you is the strains in the principal material direction. Now, you either derivatives of the strains with respect to principal material directions. Now, if you're going to go to stresses from here, then you need to go to your stress calculation, which basically stress is equal to, let me find so these are the strains in the material principal direction. You can either use this, go to stresses in the principal, not material principal, but XY coordinates, and then convert to principal direction stresses. Or you can go to principal material direction strains and then compute stresses from that. And what you use in there will typically be the same. So if I want the stresses along the XY directions from this in an individual ply, I can directly go to my laminate expression or layer expression and put the strains in there and compute. I need to show the charts from the other lecture for that. But if this is clear, I don't need to go and explain. But if this is not clear, I will go back to that, say, single layer expression tutorial. Oh, not the tutorial, lecture. Single layer. Okay, so basically, if I find the principal material direction strains, which are these, then I can find the stresses by multiplying with the Q matrix. Now, if I go and do this, then I can take the mid-plane strains and compute the stresses along the XY directions by using a Q-bar matrix. That's the reduced transform distance matrix. And then from this, I go to actually use the transformation matrix with sigma equals QX, and I put the ones in there and get the same that I want. Okay? So either way is fine, but yes, the key thing is being able to compute these derivatives. Once you compute these derivatives, then you can find stress derivatives or individual ply strain derivatives. Either way is fine. So if I find the strain derivatives along the principal material directions to get to the stress derivatives, since the relation between the stress and strain is like a Q or Q by matrix type of quantity, their derivative doesn't exist. So derivative of the left-hand side is equal to the derivative of the right-hand side. So if you know the derivative of the strain, you can find the derivative of the stress. Does this explain better? All right. So earlier it was close to being okay. Now we have accomplished something a little better. All right. So let me close the lecture again. And this lecture again. And go back to the tutorial. If I can find it. There it is. All right. I needed something that I had before that was not in version 3 of the program that you have, and I'm going to explain that. I put a new version of the composites program and explain what I've done, and you will understand the value of it when actually come to programs version 4. Okay. So to make the composites program available, I need to execute anyways this. So let me open that up a little bit better. 200 is too much, probably 150 is better. So this is a new version. I'm going to run all of it, which you will need to do. But I had another version of a matrix computation that I put into this new version. And to see the difference, I'm going to actually call the A matrix and explain it when I call the A matrix. And you'll see exactly why I needed this additional functionality that I thought you wouldn't need so far. So did I run this already? Let me run it again, it doesn't hurt. Okay. All right. So let's check if those are available. Yes, my composites is available. And the difference that I made is in the A matrix. So I'm just going to copy A matrix and type question mark A matrix and explain the difference of the new version from the previous version. The previous version took a list of angles for the complete stacking sequence. Invariant material properties, the capital U vector, and one thickness, which is same for every layer, to be the same thickness, T-ply, thickness of a ply. Well, it's possible that sometimes we actually build laminates that have multiple materials in them, therefore multiple thicknesses for the individual layers. Now, for that, thickness can be a list of thicknesses of every layer, one by one, instead of just one thickness. Okay? So if I want the 45 degree ply layer to be one thickness and minus 45 to be another thickness, I need to be able to actually do that. Okay? And you will see the reason for that once we move forward with this. Because I want to do something analytically, and this will allow me to do something analytically rather than just being limited to numbers that are kind of integers. All right, so this new capability, you don't have the capability to do this, invariant U to be different for each layer. So we're stuck with the same material layer for this A matrix. If you want to do that and expand that, you will have to do it yourself. But But let's try to set up the problem that we're working on. So the problem that we are trying to set up is we have a nonlinear function, objective function f, a nonlinear constraint. These be strain constraints or stress constraints. The objective function can be linear or nonlinear. For composites, objective function is typically, as I said before in the lecture charts, sum of the thicknesses. And these constraints take some form of a failure criterion, which is defined by the values of P, Q, and R. If it's an interactive criteria that ties epsilons, epsilon 1, epsilon 2, and gamma 1, 2 together, then these have very specific values. If it's and there's only one constraint per layer. If you use max stress, max strain, usually this will be a value, and these will be 0 for epsilon 1. This will be a value. These will be 0, Q and R for epsilon 2. So for each layer, 3 constraints. If the tension and compression limits are same, if they are different, 5 constraints per layer. But once we have that, we showed that we need something like this. So to compute this is the beginning of most of the time that I'm going to be spending in this particular tutorial, show how to compute the strain derivative, mid-plane strain derivative, with respect to ply thicknesses. Okay? And if I have this, I can substitute into here, find derivative of ply principal direction strains, and then use the cube bar matrix. I can find the stresses. Actually, I just need to use the Q matrix once I have the principal material direction strains derivatives. I can find the principal stress direction derivatives by multiplying this with the Q matrix. But we're going to come to that later on. The first order of business is to see if we can compute this guy here. And this is interesting formula that you'll see its value better as we go along. Let's try to parameterize the design activity. And for that, as I said, I'm going to use 0s, 45s, and 90s. I'm trying to keep kind of generic, but in your test, for example, you're going to be using 0s and plus minus 60s. And I'm going to define my load vector to be fixed, nx, ny, and xy. So a single point, single load design. In your case, you will have maybe a range of nx value and ny value, alpha, beta, whatever you want to do, you should be able to change that. And since some of the things that we do can be handled symbolically, I can even leave some of those parametrically. But in this tutorial, I'm going to keep them constant, single point design. The properties are AS4, and although I wrote them here, I'm going to actually remove this because I'm going to use a different material property set than what I just said. This was AS4 3501-6. I have a more generic AS4 3501, so I'm changing it to AS3501 carbon epoxy. That's high modulus carbon fibers. And I know my material properties for this. My material is ply materials AS4 3501. If I have the material, I can put it in here, compute the U vector, and my ply thickness is given to be 0.005 inches. So all the units are conventional units. So these are my given properties. Now, if you remember the test, we wrote a little routine that generates the stacking sequence for any laminate with integer layers. Okay, and that was something similar to what I have here, except this one is adapted to this particular example problem, where I'm going to treat the number of zeros not as 2, and number of 45s not as 2, and number of 90s either as of 2 or not as of 2. I think I will change the space, the laminates, a little bit. And I'm going to say, I'm going to make this M and N. Okay? So I can try 0 plus minus 45 subscript 2, or 0, 2 plus minus 45. Two variables, M and N. Only one layer of 90-degree ply, and symmetric laminate. Okay. In fact, I may want to enlarge those texts later on a little bit more. So as you can see, actually, I wrote this tutorial over the last few days, and I was in a hurry, and I even didn't bother doing these as I'm explaining. It becomes more crystallized in terms of the example. So I'm going to write the same kind of a laminate module that will take n layers of 0-degree plies and n layers of plus 45-degree plies and n layers of minus 45-degree layers and one layer of 90. So now this is a function that will give me the laminate for my specific problem. If M and N are 1 and 1, I get 0 plus minus 5, 90, and it's symmetric part. And if M is equals 2 and 2, let's say, you get 2 zeros and 2 45s, 2 minus 45s, and 190, and then it's symmetric part over here. So I have a working function to define whatever M and N value that I may have. Okay? But this module can only take M and N values that are integers, because constant array 45 and let's say, for example, let me copy this here, and instead of n equals 2, if I put 2.3, it says, hey, that is not a listable thing anymore. You cannot list 2.3 times 45. So this module will not work for non-integer values of the variable M and N. But it does work for what I want to do here. Now, having said this, I know I can benefit great deal if I can have M and N to be non-integer values. Why? That will not be a real laminate. Nobody is going to be able to build a laminate that doesn't have M and N as integers. But when I'm doing computations, sometimes I benefit from having continuous values because, for example, in sequential linear programming, I may not worry about the number of ply to be non-integer value. If I want to solve a linear programming without the integer part, I can actually solve it if I have the capability to treat M and N as real valued numbers. In fact, I doubt Mathematica, with using integer definitions for some variables, will be able to have a function in there, there is not a continuous function in terms of some of the variables. So this is something that I have not checked if Mathematica will work for integer design variables that will have functions defined in terms of them that are continuous. But that's easy to check. You can put an objective function, which is the some 2.5 times the integer variable. And if it can evaluate the objective function, that's great. If not, that's a real problem. So what I did instead, not variable amount of 9 degrees, because I want to do a design problem with only 2 variables. Later on, I can actually plot things in two design variables, but making 2-dimensional plots. And this is where I was heading with that. If I have the 9 is also a variable, I may introduce a 3rd design variable, or tie the number of 90s to either m or n, which I didn't want to do. So it's just a selection for my design problem. If you want to do a 3-variable design problem, no problem. I can actually add say mn and o being the number of 9-degree variables, and only thing I have to do is replace this line that I'm highlighting here with a constant array 90, comma o. Okay, very good. Good question. In fact, if one of you want to do that for your problem, which has 2 distinct orientation angles, we can put plus minus 60 and say plus minus 15, and have 3 design variables. just bring flavor into the test project. So I'm gonna actually do another scheme, because my problem right now, my A matrix calculation requires this laminate. Okay? But I know for a fact that my A matrix computation doesn't care whether I have 4 of these distinct layers, each with single thickness, or I have a ply 45, which is 4 times as thick, single ply 45, or twice as thick to cover both of these. Okay? So my A matrix right now does require, through this question mark question that says this is the theta, and if my thickness is thickness of a single ply, then it will require this formula. But if I get rid of this formula and build the information about this layup into my thickness information, in terms of appropriate thicknesses, then I'm good. So that's the reason why I brought the version which theta is the thickness of individual layers, individual plies in the laminate. So you'll be able to change the individual ply orientation. So if I have 2 plies of 45, I don't have to use a single ply thickness T ply. I can write 2 times thickness ply. That will cover the entire orientation angle 45s. Okay, so in some sense, what I'm doing is I'm introducing a new thickness variable, Tz, for the thickness of 45-degree plies, 0-degree plies, all of them, which is nothing but m times ply thickness, And T45, thickness of all the 45-degree plies, which is equal to n times ply T, and thickness of minus 45-degree plies, which is thickness of ply T times n, and thickness of 90, which is 1. If you were to use 3 design variables, then with O introduced as the number of 90-degree plies, that would have been O times ply thickness. Now, I have even more freedom. This TZ, TF, and TFM and TN don't even have to be integer values. So I write another function. A matrix call is now a function named my A matrix. And I put M in there and N in there as the number of plies of zeros and plus 45s or minus 45s. They are same to one another. And I don't have to write integer here. They can take any continuous value. But when I do my computation, I call my A matrix. I define a base layup, base laminate, which is the entire laminate of the distinct angles. No repetitions. Only the orientation of distinct angles, which is the only requirement is has to be symmetric, mid-plane symmetric. So my base layup, base laminate is 0, a plus 45, a minus 45, and a 90, and I take the symmetry of it. And I define my thickness of the individual layers to be m times ply, which is the thickness of TZ, n times ply T, which is the thickness of plus 45, n times ply T, which is the thickness of minus 45, and ply thickness of the 90, and it's mid-plane symmetric part, that ply T, n ply, n ply, and n ply. And then I call my A matrix calculation. The only discrete part in the A matrix calculation is the base laminate, which is discrete angles. Without repeating them, only the base orientation angles, distinct orientation angles. And all the information regarding their thicknesses is buried into this vector called T vector. Okay? So let me execute this. So let's check if my A matrix is working or not. If M and N equals 1, then my A matrix, new A matrix 1, 1, will give me in matrix form this value. So this is working and it's giving a value matrix. But let's see how that compares if I call my A matrix with single ply thickness, since every ply still in its original form is T ply thickness. So laminate 1, 1, and I print it here so that I can show you what the laminate is, and I can use that laminate in here, U vector and ply thickness. If it gives me the same matrix, then I'm good. And in fact, it does. Okay? So this one and this one give me the same A matrix. Let's check for some more eccentric laminate with M equals 1, N equals 2. My own new my matrix computation gives me 1, 2, which you can see actually it changed. The 1, 2 terms went up from 98 to 188. Okay. And if I compute the old-fashioned way of building the laminate and sending every ply to be the same thickness into this, that will have this laminate with 0, 2 times plus 45, 2 times minus 45, 90. And indeed, this is also the same. So what's the difference between these two? The difference between those two is actually when it comes to m and n, that are not integers. So if you want to try m equals 1, n equals 1.5, the new way of doing it will give me an A matrix, which is this. And if you look at that numbers, the computation is somewhere in between this matrix and this matrix here. The better way to perhaps show that would have been to use m equals 2, n equals 1 first. But the original way of creating a laminate and then using that is not going to work, because laminate 1,1.5 doesn't produce a laminate. If it doesn't produce a laminate, you cannot compute its A matrix. Just to show actually even the 1.5 does the correct thing, let me do 1 here. 1 is done here. Let's do, oh, actually I can show it here too. So this is 346. If I go to twice the 45s, I get 477. Okay, 477. But if I take some value halfway in between n equals 1.5, this 4.11 is, I believe, halfway between 477 and 346. So the new A matrix value is between the laminate 1,1 and laminate 1,2. Since the A matrix is linearly goes with that. In 346, 477, this is halfway between at 411. All right, so with this way, I can actually use m and n values that are non-integers. Now, this does not change the equation that I created here, because as you will see, this form for the derivative can be computed whether the laminate is integer or not, as long as you have an A matrix that is right and the epsilon vector that is right. But we know that this equation will work for integer thicknesses, but we also show that this will work for even continuous ones. So this equation will work for integers. That's not the point why I'm switching to this, but later on I'm going to actually be able to solve some of this analytically, so that I'll be able to show some things that will really show trends in the design, rather than limiting ourselves to only integer values. The additional advantage, of course, is if I'm able to compute this A matrix for a non-integer value like this, that means I can even put parameters in here instead of integers or real numbers, and get my A matrix parametrically. How? Well, that's easy. I call my A matrix, with m and n, and come up with this A matrix, which is a function of m and n only. Now this looks a little bit cluttered because of these standard -18s and so on and so forth. If I write that in matrix form, it even is a big matrix appears, at least, where A11 term is this one, and A12 term is this one, and A16 and A26 are 1, 3, 0, and A22 is this long term here. So I'm going to actually take these terms and simplify them. A matrix 1, 1 is the first element of this matrix, A1, 1, A through A 6, 6. And you'll see that actually they are much simpler when you simplify them in terms of m's and n's. And if I redefine my A matrix in terms of m's and n's, just for this particular problem, my A matrix is just this. Very nice function of m and n that are actually continuous values. Okay? So I can actually analytically take derivative of the A matrix. Okay? But that's besides the story. And finally, we'll be needing an objective function. And that is in terms of total number of plies. I don't have O for the number of the 90-degree plies, counting that, so I put 1 in there. But m times 2 times ply is the total thickness of all 0-degree plies throughout the laminate. 2 times n times 2 times ply is total number of 45s. It's minus or plus. And this is the thickness of 2 plies of 9-degree. And this is going to be my objective function. This is what I'm going to be trying to minimize, either with discrete values of m and n or continuous values of m and n. Okay? So this is where I think sequential linear programming and sequential integer linear programming is going to come handy. All right. So now let's get to the derivative calculations. All we did so far is we showed that we can get the A matrix. Of course, if I want to do A matrix evaluated at m goes to, say, 1 and goes to 1, I get the A matrix for m equals 1 and n equals 1, which we already found up here. This one, these values, same values, 346, 9, 83, 346. All right, derivative calculations. Now we are ready to evaluate the derivative of mid-plane strain with respect to the ply thicknesses. Okay? As I said, this formula should work if I have the A matrix, whether I have an integer design or continuous design. But let's see. This equation doesn't care. As long as you have these quantities on the right-hand side, of course, getting the right A with just a constant is going to be tricky. And getting the A matrix in terms of m and n, we can do it. I mean, not tricky, but straightforward. Getting it in terms of m and n will also be straightforward, not too tricky. And epsilon will also compute. To demonstrate this derivative, I'm going to pick an integer-based design. Let's say m equals 1 and n equals 1. And again, just for demonstration purposes, I'm going to use a loading, which is nx, ny, and xy equals a fixed quantity. Now, this doesn't have to be fixed. This can also be parametrically define in terms of some value of alpha or beta or whatever you want to put in there. So that's up to you, but I used the constant value for it. This is what I'm wanting to highlight. So in your test, if I ask you to change these parametrically, either continuously or some discrete values, you should be able to do that by redefining this load n properly. So I don't remember if I executed this or not, so let me execute it again. Load n is now 4,000, 1,000, and 0, and x, and y, and xy. And I'm going to do the analysis of the base design and find the derivatives of the base design using the traditional with integer values. Okay, and for that, I need the limit 1, 2. That's what I'm demonstrating at this base point, and compute the A matrix with these integer values. So this is derivative is going to be computed about this laminate with m and n values of 1 and 2. This is the A matrix value. And if I want the midplane strains from this, I inverse the A matrix, dotted with the loads, I get the midplane strains. These are my midplane strains, which are 0.0089 minus 0.0014, and then 0. This is practically 0. My derivative equation says if I want the derivative of the midplane strains with respect to a particular orientation and angle, then you take the inverse of A matrix with a minus sign in front of it, and multiply it by the Q bar matrix of that orientation that you're trying to compute the derivative, multiplied with epsilon super 0, which is the midplane strains. So that means I need 4 different Q bar matrices, one for the 0-degree ply, and one for the 45-degree ply, and one for the minus 45-degree ply, which is going to be very similar to the 45, with one difference in the 1, 3, and 2, 3 terms, and the 9-degree ply. So the Q bar matrix, this is the same as your test. There are 4 Q bar matrices in this. The first Q bar matrix is QB1. That's the first Q bar matrix. And the Q bar 2 would have been that. And the only difference between Q bar 2 and Q bar 3, you will see that just a minus sign in front of the 1, 3, 2, 3, and 3, 1, 3, 2 terms. So if I want the derivative of the strain, partial strains, I'm taking derivative of all 3 strains with respect to the first orientation thickness. Therefore, I use QB1 here. Dotted with the midplane strains, this is the formula. This is this formula here. I should get derivatives of epsilon 1, 1 in the 0-degree ply with respect to the thickness of that ply. Here, this is the epsilon 1, 1 of the 45-degree ply with respect to thickness 2, but this is epsilon 2 with respect to design variable of the 0-degree ply. Okay, so there are 3 values for each of these, because these are basically epsilon not 0, which is bold-faced here. This is epsilon midplane x, epsilon midplane y, epsilon gamma midplane xy of the ply with the 0-degree orientation angles. So these are not the derivatives of the principal strains. Did I say that earlier? Principal strains. These are not the derivatives of the principal strains. These are partial strains, midplane strains. In fact, I should have probably represented as partial midplane strains. Partial midplane strains and partial midplane strains. Partial midplane strains. First one with respect to thickness of the 0-degree ply. Second one is with respect to thickness of 45. Third one with respect to thickness of minus 45. And fourth line is with respect to 9-degree ply. Midplane strains are already computed as the baseline. Okay, so these exist above here, and each calculation is the same vector. Inverse A matrix is computed or computable. I already used it in somewhere up there, I think. No? Oh, here. Okay. So inverse A matrix also exists, and these are the derivatives. Now, what if my variables were non-integer? Then my A matrix is actually, I have it in terms of M and N, okay? And if M and N goes to 1, I get the same, the baseline, M goes to 1, N goes to 2, I get a numerical value for it. But it is actually exists in symbolic form as A matrix. So my midplane strength, I compute inverse of A matrix symbolically, and I can show you that it's actually Messier expression. You see, just the A11. If I take percent, this is A11. Derivative, I mean inverse of the A11. A11 inverse. You see that it's a very complicated expression. Well, it is there. So if I dot that with the load N, which is constant, I get all the midplane strains in terms of expressions. These are also fairly complicated, but by putting the M value of 1 and N value of 2, I can compute the derivatives. Yeah. Why these two lines are repeating themselves, I don't know. Oh, I know. Okay. I just wanted to show that actually, though the strains are here, let me do this first without evaluating at a particular value of m and n. So mid-plane strains are here. So what I need is, say, one of these. Without using this construction. So not for all four, but just one of the derivative vector is this. Okay. So it's it has the inverse of the A and multiplying that, and the inverse of that, and multiplying it, and at the end you get a big, huge mess of numbers in terms of m and n. But in fact, if I put m and n 1 and 2, I get exactly the same values that I computed above with the traditional approach of the derivatives. Just to compare, I'm going to copy these from there to the bottom of this, just to show that the two different ways I get the same results. 0.44 minus 0.4, 170. They're the same, except this is a bit cleaner. Instead of type minus 18, and it shows 0, and that's the only difference. So what's the value of what I do with these m's and n's? And that is when m and n is not an integer value. In fact, I can compute the derivatives of the strains for, say, n equals 1.9 instead of 2. The traditional way will not allow you to do this. Here's the derivative of those with respect to individual ply thicknesses, and for n equals 1.9. It should be close to somewhat to these, because this was for 2 and these were for 1.9, and that's the point I wanted to make, that it's actually minus 0.44, this is 0.46. This is 0.099, and that is 5 minutes. Very good, Claude. Thank you. This is minus 1.0. So fairly close to these, but I now have a way to compute derivatives at any design point, value of m and n, compared to the traditional way of dealing with only integers. So what is the point that I'm trying to make here? The value of this is not going to become obvious until we really compute the linearization, which is really doing this. And then designing with it, with continuous variables versus discrete variables. In fact, discrete variables, we won't be able to put into, I believe, integer linear programming. We may be able to put it into the linear programming, but no, that won't, because we need to compute a matrix at any point in the design optimization. So we're kind of needing this capability of getting the derivatives with respect to design variables, which are integer. But it's going to enable us also to do integer linear programming, to do sequence of linearizations, and go with those, because we'll be able to write those expressions, these linear expressions, as continuous variables, even if our approximation is going to be continuous. So you will see that when we come to the integer linear programming, we'll have a branch. I understand our time is up, but I'm not talking about the rest of this tutorial now. I'm talking about the general conceptual matter of how you go into the design of sequential linear programming. You can create the sequential linear programming problem and solve it using any linear programming. The answer is not going to be integer. Then you keep repeating this until you approach and converge to a non-integer design. You can do this without requiring this capability to have integer values. And at that point, in the final point, you can probably call integer variables and be able to design it. Or you can implement integer linear programming at every iteration and always jump from one integer value to another. And then relinearize the problem. And what I would like you to see at the end, whether these two different approaches are going to give you the same result or the different result. And that will be the reason to do what we're doing right now, going to the linearization of the failure constraints and implementing it. And my implementation of the failure constraints would be max strain criteria to make things simpler by creating 5 constraints or 3 constraints for each ply using this expression. So I'm going to stop here and answer any more questions that you might have. Questions? So we'll have at least one more lecture before I can say, okay, the test is ready, and go, and you'll have another couple of weeks or so to finish the second test. Which is a very interesting project because for the first time you'll be able to handle a composite design problem which is nonlinear, which most design problems are, and find an answer that actually makes sense, which is integer design at the end, not continuous design. Any questions? I'll ask one question, if you didn't think of this question. So far, we have been demonstrating it with thickness variables. What about my orientation angles? If they were the design variables. But I know that I don't want continuous values. I want discrete values of the ply orientation angles, like 15s and 30s and 45s and 60s, and not 35.7875. But everything that we are doing right now is going to work for that. It will if we can get this thing computed, the derivative of the midplane strains with respect to orientation variables, tail sub I. And there, you're going to see that actually there may be some issues in there, because orientation angles are now in these Q's and Q bars. So the Q bar is not a constant quantity for orientation variables, but it is actually a changing quantity. So that goes back to, let me go to my lecture. To here, I may be able to evaluate these, and and but the A matrix now is a function of not thickness being linear, but this is going to be a nonlinear term because it will have cosine 2 thetas and cosine 4 thetas. Do you know a way to get linearize the Q-bar matrix? It's a question to everybody. Think about this. Do you know a way to make the Q-bar matrix expressed in a nice linear fashion? Any answers? Let me give you a food for thought. What do you think the lamination parameters are going to do? What is the lamination parameter? V1 star, V3 star. Ah. How about that? Think. With that, I'm closing the lecture. I'm going to stop recording it. If there are no more questions, if you want to be on the record, ask a question now. Did you get my email about my issues with my copy of Mathematica? Samuel, no, I have not seen that particular email. That's interesting because I did see this morning emails from Murray, who sent me an email this morning, who may not be here today. No, I will check my emails. If I don't have an email from you, I'll write you back, okay? Any more questions? Questions are closed. Camera is closed.